For this tutorial, we will be building a pipeline to find and select worms for creating a worm module. This is the pipeline you would want to run if you are creating a model for the first time, and can be omitted if a previously created model fits new data. This is the pipeline you would want to run if you are creating a model for the first time, and can be omitted if a previously created model fits the new data. To begin, start CellProfiler 2.1, or alternately save any previously created projects and then clear the pipeline. The CellProfiler interface consists of the pipeline panel to the left, which is divided into input modules and analysis modules. A space for module nodes for annotations, and a file list will appear to the right. To provide CellProfiler of image files to be analyzed, drag and drop the input image files into the file list space. For the model to be able to handle the variability in shape seen in a broad spectrum of phenotypes, we start by selecting a few images from each of the L4440, DAF2, and PEB1 phenotypes. The goal is to find approximately 40 to 60 non-touching worms as input for training the model. For the current dataset, select 3 images from each gene. For example, you can use all the images from wells in row D of the plate. The input module metadata enables extraction of metadata from file names and folders. In this case, we aren't making any measurements and can therefore omit metadata extraction. Next, select the input module names and types. Set the input image type to color image and assign the images the name RawData. No grouping is needed, so the groups module can be omitted as well. In order to save the worm model, you will need to adjust the output settings. Click on the View Output Settings button in the bottom left of the CellProfiler interface and then adjust the default output folder to point to the folder where you want to store your output. Once the input modules are set, the analysis pipeline is built up by inserting modules into the analysis panel. Modules are added by clicking the plus sign next to Adjust Modules in the bottom left corner of the interface to bring up a list of selectable modules. Most object detection methods in CellProfiler are designed for bright objects on a dark background. Since the input images are color images with a bright background, the first thing we need to do is to invert the image pixel intensities, adding the module called ColorMath located under the module category ImageProcessing. Add the module by selecting and double-clicking it. The module has now been added to your analysis pipeline. When the module is selected, its settings are shown on the panel to the right where they can be adjusted. For this module, select invert as the operation, call the output image InvertedRaw, and select RawData as the input. Most image processing algorithms operate on grayscale data, so the next thing we will do is convert the inverted color image into a grayscale image in 2 different ways. First, we add the module ColorToGray, and then combine the red, green, and blue channels of the inverted raw image into a single image that we will call OrigGray. The image will be used to identify the worms. To see the effect of a module, click on Start Test Mode. It is now possible to step through the analysis pipeline and monitor the output at each step. Add another ColorToGray module, and this time split the red, green, and blue channels and call them OrigRed, OrigGreen, and OrigBlue. These images will be used for identification of bubbles and fatty regions. As it turns out, bubbles have high contrast in the red image channel and appear brighter than the worms in the inverted image. The same is true for the edges of the wells visible in the corners of the image. We can detect both of these structures in the OrigRed image using the object identification module IdentifyPrimaryObjects, using a manual intensity threshold of 0.5 and allowing a size range from 10 pixels to 10,000 pixels. Make sure not to discard objects touching the border of the image, as we do not want to lose clusters of worms where only one or a few worms are partly outside the field of view. In this case, we will not attempt to separate touching objects, and we will call the output well and bubbles. We also want to remove shadows surrounding bubbles and well edges. To do this, we will add the module Expand or Shrink Objects and select Expand Objects by specified number of pixels, and expand the well and bubbles object by 5 pixels. We will call the output Expanded Well and Bubbles. Next, we use the mask image module to mask the OrigGray image with expanded well and bubbles to get a new image, masked gray, without artifacts. Make sure to invert the mask in order to keep worms and remove artifacts. We will now use IdentifyPrimaryObjects to separate worms and worm clusters from the image background. With the masked gray image as input, we set the size range between 20 pixels and 30,000 pixels in order to remove small debris and ensure that large worm clusters are kept. We use automated thresholding with global robust background as the method. Since there is a risk for empty wells, we also set a minimum threshold level at 0.09. In this case, we will not attempt to separate touching objects. Uncheck the Fill Holes in Identified Objects setting. Finally, we will give the name Worm Objects to the worm objects. We can view the worm identification results by stepping through this module in test mode. At this point, both single worms, clusters of worms, and possibly some debris have been identified as worm objects. It's worth mentioning that the identification steps are the same as in Pipeline 1. The same preprocessing and foreground-background segmentation should be applied both when creating the worm model and when running. In this display, the individual worm objects are assigned unique colors. In order to create and train a worm model, the next step is to manually select all single worms from each image. For this step, we use the Edit Objects Manually module, with the worm objects as input and selected single worms as output. Optionally, you can use RawData as a guiding image to make sure our selected worms represent true worms, but sometimes outlines are easier to see against a black background. We'll take a closer look at how Edit Objects Manually works when running the pipeline. Once the single worms have been manually selected, we want to save them so that we can build our model and, if needed, add more worms to our model in the future. Prior to saving, the Convert Objects to Image module is used to convert the worm objects to a binary image, calling the output image worm binary. Then we'll use the Save Images module to save this worm binary image, with RawData as the image used to name the new file, with the suffix _singleworms. At this point, we can run a pipeline to analyze all the images, but first we have to exit test mode and select Hide All Windows on Run in the window menu. Then click the eye icon for Edit Objects Manually, so the result for that module shows up during the run. Next, run the pipeline by clicking the Analyze Images button. Once the pipeline reaches Edit Objects Manually for the first image in the cycle, an editing window will appear. Here, the goal is to use this interface to select all single isolated worms that do not touch a neighboring worm and do not touch the image edge. This is done by clicking on each single worm. Once a worm has been clicked, its outline becomes dashed. The zooming and panning tools can be used to better see the outlines of the individual worms for selection. When all single worms have been selected in the image, click on the Reverse Selection button. At this point, only the single worms will show up with solid outlines. Click the Done button to finalize selection. The selected worm objects will now be retained for saving by Save Images, and the next image in the list of input files will be processed. As mentioned earlier, picking 40 to 60 worms that are representative of the variability of sizes and shapes observed in experiment is recommended for model training. At the end of the pipeline, the output folder will contain images of the single worms you have selected. It is wise to do a sanity check of the selected single worms when the analysis is done by browsing the output images. It is very important to include only true single worms during the training, as non-single worms will make for a less accurate model. Any errors can be corrected by rerunning the pipeline using that particular image as input.